Hello, everyone. This is hopefully the last part of the image processing module in the machine learning for image processing course. In the last class, we were discussing about how can you like detection of edges you can do through gradient computation. And for computing this gradient, in the last class, you have seen the finite difference scheme based kernels for doing that. Of course, we haven't yet written as a kernel in the previous class. That's what we will do in this class. But you have seen, suppose if you use a finite difference scheme and then your dou f by dou x, a discrete version of that will be equivalent to, let's say, f of x plus 1 comma y minus f of x comma y whole divided by 1 there. Similarly, we have written for backward difference scheme as well as central difference scheme, right? Say, for example, now it's a linear operation, is it not? This derivative is a linear operation. So when you want to do this, you can do it using as a mask array kernel. You could write it as, for example, take this itself. Then f of x, let's also consider this is your x and this is your y direction. And then your x plus 1 comma y. So here, this consider this is your center here. Then what would happen? Your x plus 1 comma y is this. So consider as if you are keeping this center at every pixel of your image, whichever image you have. Okay, at each pixel you are taking it. And if I am computing a cross correlation in order to compute the derivative or convolution, both these are two are like dualities, interchangeably you could use. Do you think, is this a mask for convolution or a correlation? I have given you the center. Now, can you tell me, I have an image of f of x comma y. Should I convolve with this or correlate with this mask? I have given you this mask also.
It is a correlation mask, sir.
That's right. It's a correlation mask because you are simply multiplying it. If you are doing flipping, this is what you see. If you are multiplying it, you notice at each pixel, suppose here is my pixel x comma y for a particular values of x comma y. You notice that this is exactly doing this if I am right away doing it. If I want to convolve it, then I need to flip it. So this being my center, this is here. So I need to compute the other way around. So typically, these two are different because this mask is not symmetric. On the other hand, we have also considered a central difference scheme where I'm sure now I don't want to write that fully. This is x minus 1. There were 2 are there. Instead of that, I will get 2. Okay, this 2, I could absorb it into the weights of each kernel. And it's not difficult for you to figure out when this is your center. This is a very symmetric mask. And if you are using a central difference scheme, the mask that you get is a symmetric mask, and thus both convolution and correlation means the same there. Is it clear? But of course, one of you are mentioning it in a slightly different way. You could in fact shift the image and then also do a subtraction. That also is possible. Will give you a similar result there. You can otherwise do it in this manner as well. Okay. Now, assume that, let's again, for the sake of simplicity, let me go back to a 1D version of applying this. Anyway, we have discussed at length in the previous class. It is the gradient that you would compute in case of a 2D. That's nothing but a vector that gives you dou f by dou x, comma dou f by dou y. Of course, if you want to write it as a column vector, put transpose there. That's what the gradient you have it. Okay. So that's how you deal with the 2D case. And then magnitude will be square root of the magnitude of a vector is the magnitude that you would assign here. Similar to you find a orientation for a vector, you do the same for this gradient also. Now, suppose I have a step function like this. Okay. So you are doing all this stuff. Okay. You have seen two lines there, but assume it's a single thick line there. Okay. Yeah. So you are doing all these things. Why are we finding out derivatives and gradients? What was the eventual objective there? What for are we doing?
To find the edge.
That's right, to find the edges. Now, suppose I have taken one row of your image. Its intensity profile is something like this I naught. Suddenly there is a jump of I1. This is my X value. As I am varying my X, this is how the profile of intensities is on Y axis here for me. So that's how it is. Okay, you could consider the center here if you want this to be starting from there. That's all right. That's where varying X, I'm plotting the intensity values there. Now, if I apply a, let's say, simple case, forward difference scheme I'm applying on this, and I want to find out here dou f by dou x, I want to plot here with varying values of x. How does it look like? Let's first look at values still here. What would be the value still here? Let's
0.
call this as x naught. Okay, so that I could easily refer to it. Till x naught, what would be the profile?
It will be 0, sir.
0.
Correct. Very good. This is 0. Okay, just let us leave at the boundary. But again, after this region, what would be the profile again?
Again 0.
Very good. What would be the immediately here after this? Will it be, what would be that value?
Be I1 minus I0.
Very good. Is it positive or negative?
It's positive peak. I0.
Correct.
I1
Very
minus.
good. Very good. Very good. That's right. Because you are using forward difference scheme, here you get I1 minus I0. What about the one on this side here? Just next here. For a pixel here, so, well, when you are here, this minus this would give you a peak here. Okay. That's all. That's how you would get it. And of course, if you are using a central difference scheme, you could also get something like this. Also might get you depending on where exactly you are computing. But you could simply see a peak there because that there is a difference you could find out. Now, we have seen that it's very common that images could get corrupted by noise. So assume that a small percentage of noise, a constant percentage of random noise got added to this profile. Now that's the small noise that got added up. Okay. Now, if that is the case, yeah, this is a step one. So perhaps here it is right. I will get just a single peak here. Just think about another profile there. This is assume this is my profile. Can you tell me what would be the profile of dou f by dou x here? Let's first see till here. What is the profile till then? Dou f by dou x?
0, sir.
Very good. And what about here? Again 0,
0.
isn't it? Correct. So what about here? So you are subtracting from this forward difference, you are taking from this value, you subtract this. So this is a positive slope. So what do you get there essentially? What would be the output there?
Constant slope.
Yeah, constant slope. You tell me how the profile here would look like, dou f by dou x. What will happen here? Will I get a ramp here or what do I get there?
Rectangle.
Straight lines.
Correct, correct. Like a rect function, right? Good. This is what I would be getting there. Correct. Well, you could do it for some other different shapes also. You could figure out essentially this is giving you how much the derivative is there. So the derivative, the magnitude of that is equivalent to, will give you in a way where there is that slope will tell you how it is varying, and you could make a lot of inferences. So let's not go into those details in the interest of time. But the point I want to particularly convey here is, even adding a very small amount of noise here, this is what the dou f by dou x you would be getting. While here in the f of x, it's very clear for us that there is a jump there. See, even around 0, this change versus this would eventually would give you something like this, out of which figuring out this edge and getting that is a non-trivial task. That's not possible, in fact, in the way that we are looking right now. What could be the solution to deal with this thing? See, for us, it is so obvious when you see f of x where the edge is. On the other hand, when I'm going to the derivative of f of x, that's not so obvious. So what should be done here? To deal with such images where there is some noise got added because it is messing up in finding out the edge that is originally there in your image. So what can be done to deal with such images?
Averaging filter.
That's all. You do an averaging filter, or even better, you just go for a Gaussian smoothing first. Once you do a Gaussian smoothing, right? This is a randomly varying noise. It's not a constant noise that got added. That's what would happen in most of the cases. Hope you realize why this part has been excluded there, because there is no information of yeah, you could actually same thing, reflection if you do, or some boundary condition if you do, you can deal with it, but for the time being, don't worry about that. So what would happen? This somewhat strong edge because of Gaussian smoothing. There is nothing wrong if you use weighted averaging. Things also would reasonably give you good result there. So you are getting something like this now. Now after that, now you apply a derivative here. So obviously at the center, it will give you a peak here. A peak in, so what is now going to happen? Wherever your derivative is maximum, that is where there is an edge. So in order to deal with images in which there is some noise that got added, you simply need to use a Gaussian kernel. Of course, if your noise, the kernel size would dictate on whatever the level of smoothing that you would get there and other stuff. So that's based on that, you would figure out a kernel. There is no magic that tells you exactly what is that. You should have either some prior knowledge, or typically you do empirically, or there are some non-trivial advanced methods that you could use to figure out what should be the kernel. Anyway, that's not the scope of our discussion right now. But the important point I want you to convey is that a peak in dou by dou x of h convolved with f, where h is a Gaussian kernel, in that the peak will tell you where the edge is. So the message here is that the derivative operation, or I could say a gradient operation, because after all, that's a derivative. It's a vector containing the derivatives in both x and y, is very sensitive to noise. Hence, it is typically applied after convolving it with a Gaussian. That's the important take-home message here. Well, suppose I have a here, let's say its size is number of signals there. Let me call it as n. Okay. Now, assume that my kernel is of size k. This kernel is of size k, Gaussian kernel, or let me call it as k1. Then on top of it, there is a kernel h here, dou by dou x, could be again another kernel I'm going to apply. Let's call that kernel size as K2, right? Now, what is the order of multiplications? So assume that there is some padding you are doing to deal with boundaries. So don't worry about those small incremental change that will come in your computations. Assume that you are buffering and doing it for the entire change. The assumption here is n is pretty large compared to your K1 and K2. So that doesn't really matter. My question here is, how many multiplications, what is the order of multiplications that would be required to arrive here from here? From here.
N into K1, K2.
That's all. Here to arrive here, this is order of n times K1. Okay, because you at each pixel you put this kernel, you multiply the respective elements, isn't it? So there are, your size of your kernel is K1, so there are K1 multiplications and K minus 1 additions that you are doing. Anyway, compared to additions, multiplication is critical, so I'm just taking here the multiplication part. Then from here to here, how many multiplications are required now? Given this, okay, now I want to do, now I need to do a derivation there. I need to do a derivative of that. I need to compute. Depending on whether you are using a finite difference or a central difference, assume that the size of your kernel is K2. From here, from here to here, you just tell me, or overall now you tell me, both put together. Order of, earlier it was n times K1, now how many?
N times K2, sir.
That's all. It's a very, I'm expecting more aggressive or more active answers from you guys. Right. Order of n times K1 plus n times K2. Or I could write it as order of n times K1 plus K2. Okay. Suppose I have 1,000 by 1,000 image. I'm just talking about one here. So 1,000 times K1 plus K2. Okay. Now, so what I'm doing here is F convolved with H, and the whole thing I am convolving, the result I am convolving with a derivative. Okay, or I could, let me call this as H1 convolved with H2. Can you make use of any properties of convolution in particular and bring down this computational complexity? Or is there, first think, any other alternative way of arriving at the same result in terms of your output, not in terms of your number of computations required, but in terms of the output? What can you do there? What property can you, in what different way can you do the same exercise?
So first we will differentiate the kernel. Then
That's all. Very good. So what I will do, in fact, is F convolved with H1 convolved with H2. What is the advantage there? H1, or I would say, so this is same as this commutative property or associate. I think this is associative property, right? It's referred to as, this is same as this convolved with H2. You all know that. So I would take a derivative of this Gaussian, and that's what I would apply right away on my F. Suppose, what are the number of, if I am taking the derivative, so this is what, this is the derivative of your Gaussian. What would be the order of multiplications required to compute the derivative of Gaussian now? You tell me that number. Okay. I'll write the answer and you tell me why is that answer correct. I write here order of K1 and K1 times K2. Now you tell me why is that so. Why is the convolution of H1 with H2, the number of multiplications required are of the order of K1 times K2.
Sir, because K2 multiplications will happen for each of the K1 pixels.
That's all. No, as simple as that. Assume that you have this as, let's say, for simplicity, I'll take this as 4, this as 4. At each pixel, you are doing 4 multiplications. So 4 into 4, you are doing 16 multiplications overall. Now, this, again, let this size of that will be, for example, whatever you are getting as a result of it is, let's consider it as almost of the same order, right? At each pixel you do it and you put it there. Let's say, let us call it as K1, approximated K1. It will just vary with maybe some value here and there, but let's call it as K1. So what is the order of now multiplications required? Okay, or maybe let me call, to avoid any confusion, let me call the size is K3. Okay. Now, what is the computational complexity in terms of multiplications when I convolve f with K3? This is of size n.
In K3s.
Right. N times K3. So what is the total number of computations now? Order of K1, K2 plus n times K3. Okay. Assume your n is 1000. So this is each of them as, let's say, 10. Okay. So 10 into 10, 100. Plus this also you consider 10. So 10 times 1000, 10,000. So essentially it's the order of 10,000. What about here? You have 1000. K1 plus K2 each is 2. Okay. Each is 10 into 10, 20. So you would eventually reduce it significantly. Number of 1000. 10,000, 20,000 here required. On the other hand, this is more. Now you think of it now, this is 20,000 for one row. Okay. Such things are there now for 1,000. You need to do it 1,000 times for all each row. Okay. 1,000 rows. So you could see that there is a significant reduction in number of computations that would be required when you make use of this property. So this would be, for example, a Gaussian. This again, you don't need to do it every time. You know what is the kernel. You right away use that kernel. So that way I could even drop this out. Okay, this is not required. In fact, it's just n times. It's almost like doing one convolution. Now think of it when you need to do it. For example, a sequence of some 5-6 filters are to be applied. There you will see it much better here. Okay. So that's how you would now, instead of doing with a Gaussian first and then a derivative kernel, you right away do with this. This is a derivative of the Gaussian. You could see here at the center, the slope is 0. That's where this would come like this. And then its behavior till here, the slope versus this, roughly you could see it in a different way. That's why it keeps on increasing, then decreasing, and then increasing kind of stuff. Okay, it's not difficult to visualize that. Then you do it and you would of course arrive at the same result. You just leave then in the output to find out the ones with high derivative as where there is a high transition. So you simply find out the maximum now. That maximum would give you the edge there. That's all. Just take you through one more step also. Okay. So then suppose if I do a, so in order to find out a maximum, right? You just, if you take one more derivative here, okay, you expect some maximum here. So if you take one more derivative, that essentially will give you a zero crossing here anywhere, right? So that's how you could slope. If it is maximum means again one more derivative, that is where your slope is again 0. Slope is 0 means you need, if you take one more derivative, that would give you a zero crossing here. So people typically use second order derivative, and as it is easy to in a way it is easy to compute the zero crossing, people do this. And in order to find out where there is a strong edge, all you need to know is to find out a zero crossing. Again, what can be done? See, one more derivative you are taking. So still you do a single convolution now with f, because this size of the f is much larger compared to these things, and all you need to do is take one more derivative of this function, and that will give you this function, and you die right away, convolve your function with this, and then you find a zero crossing here where there is a maximum. Zero crossing means from negative to positive. This is not a zero crossing, it's a zero. So from either from positive to negative or negative to positive, you just simply compute where this is happening, and that will tell you where the edge is. Does anyone from medical imaging course remember the name of this shape? What is the shape? Inverted Mexican. It's an inverted Mexican hat. Okay, it looks, you look at 3D, assuming it's a symmetric kernel that looks like a Mexican hat but inverted. Okay, that's how this is referred to. Okay, or can
Sir,
if
for
not,
both first order derivative and second order derivative,
hmm.
is number of multiplications are same.
Yeah, you yes, it's just the one more time you are finding out derivative, right? So that's, see, the keep this in mind. Maybe you need to take care of your boundaries. That's once you ignore that part, and this will be of same size, right? More or less. See, it's a 10, 20, becoming 20 doesn't really matter, even if it is a little more you are getting there, because your image size is 1000 by 1000 or could be more. So that will be the same thing. You just compute it for that region, assuming that you will take boundaries. This is all you will get it there. Inverted Mexican hat is something you would get it. So see here, for example, it is varying from 0 to 400. This is the shape you have it. And finally here also within 0 to 400 you are getting that. That should be good enough. Is
Yes,
it
sir.
clear? Yeah. Any other question? So essentially you are computing dou square by dou x square of h convolved with f. In order to do that, you are doing dou square by dou x square of your h, right? H is your Gaussian kernel. So it is a second order derivative of the Gaussian kernel. That's all you are taking here. This is the first order derivative. There is a Gaussian here. Okay, very badly drawn there. From that, you take the derivative. Second order derivative looks like this. The first order derivative looks like this. Second, one more time, you take the derivative. That looks like that. Okay. So let me now go to another. Typically, you won't really have to use this in theory is fine, but there is a better way. There are some well-defined or predefined kernels that you typically use for computing these derivatives in the horizontal and vertical directions. I'm simply saying derivatives in horizontal and vertical by the time already getting gradient, because the vector of derivatives in the horizontal and vertical will give me the gradient. Okay. So ignore, in the interest of time, I'm just ignoring Robert, because anyway, it's just for historical purpose. I kept it there because that's one initially proposed in 60s or something around that. But I would rather draw your attention to Prewitt and Sobel. Okay. Now, the way you could look at it is, this is your X, this is your Y, did that. And this would give you, these are the kernels that are used for computing the edges. Okay. So basically, can you make any guess on which edge that this kernel convolving, or let us call it correlation now. By correlation of this, when you correlate your image with this, what is the edge that will be found? Can you make any guess? Is it a horizontal edge or a vertical edge? Let me keep it that way. Horizontal, vertical, two
With which
possibilities
kernel,
here.
sir?
This kernel,
Horizontal edge.
correct. So very good. So assume that there is an edge here, right? That means when you move along this edge, there is no difference in intensities. If it is a horizontal edge, this is a horizontal edge. There is no difference in intensities when you move along the edge. But on the other hand, it is here when you take difference of pixel here versus here, that is where you find out a difference there when you have a horizontal edge present. So you are moving, say, I show you this, okay? When you move from, so there is a sudden transition here. When you move from here to here, if you are moving along this, there is no problem. But consider just a thin edge, okay? This is a bigger edge, but assume a thin edge. When you compare here, before and after, that's where you have a transition there, correct? So that will tell you the edge. So I wish I have some images, maybe not here, but that's okay. I'm sure you'll be able to visualize that. So that means if that is a correlation mask, it's equivalent to f of, just consider for the time being this part, okay? So that I can write it as f of x. Consider this as your center, okay? Then give me the expression for that. F of, what does these two imply? F of x comma y plus 1 minus f of x comma y minus 1. Okay, I'm uniformly dropping the multiplication factor. Otherwise, you could consider a multiplication factor of by 2. So you are finding out a derivative there, essentially. If you ignore the rest, this is equivalent to computing a derivative in the y direction, and this is giving you horizontal edge. But now, in addition, what I am doing here is I am repeating the same exercise for a pixel which is to the right of it, and the same exercise I am doing it to a pixel which is left to it, and then summing up. So this is in a way what, so that means I have a derivative dou f of, let's say here, x plus 1, okay, by dou x. I'm dropping it y because y is same for all, so I'm just not drawing it there. And then I did same derivative for x minus 1, or if I call it as x, this is x minus 1 and this is x plus 1. And when you are doing this correlation, that means finally you are going to add all those things. So essentially, if you notice there is a smoothing operation also applied on the derivative. So you notice here, there is a smoothing as well as horizontal edge detection, both put together is happening here. Could think of it as an average smoothing, okay, with same weight there. Same concept you could see, this is the one which would find you the vertical edge, because you here you could, any mistake did I do there? Yes, that's fine. Here, this is like, now you pay attention here. This is equivalent to, hope you are all following with me carefully. This is equal to x plus 1 minus f of x minus 1, right? You are doing the same thing for a, you are finding out the vertical edge here. For this location, you are doing the same thing for a pixel above it. For the vertical line, you are doing it above, below, at this point. And of course, when you are correlating it, you will finally add up everything, right? So if you write it, everything put together, you are kind of making an average. So earlier, one way is you could do an average of intensities. That is one way. You could interpret this to get some intuition about that as you are now doing an average after performing or after computing the derivatives. So the first one would give you a horizontal edge. Second one would give you a vertical edge. They remain horizontal and vertical even if I change this y to x and x to y. Okay, that will still remain same. These are the correlation masks. Convolution mask, well, it would vary, but correlation is good enough anyway. At the end, you consider it as an edge of equal priority, whether it changes from dark to bright or bright to dark. That's all this would change when you are doing a whether correlation or convolution. Other than that, there is no difference. And when you are finally computing the magnitude, it doesn't really matter. Okay, is this clear? Did you get some intuition on why the first one would give you a horizontal edge and the second one would give you a vertical edge? Is that clear? Right. So anyways, now if you look at the, so now I want you to give, if you have understood that, I want one of you to give an interpretation or an intuition for Sobel edge detection.
Sobel is giving more weight to the central pixel.
That is all it is happening. It's like a weighted average now. You give more, double the weight to that center one here while you compute the derivative, because now this is like multiplied with 2. This you multiply with 2 and this multiply to 1, these particular columns. And similarly for a horizontal or for a vertical edge, again, for the derivative computed here, you multiply here. Okay, otherwise here you took it, you multiply here with 2 and this with 1 and this with 1, means you keep one multiplying it with 1 means you retain the same. That's what will give you a Sobel. It is more like your Gaussian averaging or weighted averaging, where you give more weight to the pixel that is of interest to you. This you are doing to compute. So in this center, you keep at that pixel where you want to compute the magnitude of your horizontal edge or the magnitude of your vertical edge, if it is the other one. So it is at that pixel, whichever pixel you are looking at, that value of derivative which you are getting, you are giving a weight of 2 for the one, the compared double the weight you are giving, then it's neighboring pixels. If it is a vertical edge, right, while you are computing it this versus this, you are doing it, and the other way for horizontal edge. And just for sake of completion, let me also talk about quickly about this robot. It essentially finds out edges in the diagonal. So if you look at, so well, this mask defined is slightly different. These are not symmetric here. Okay, there is no symmetry there. But at a given pixel, you could see this one, this minus this, or this minus this. So that would essentially give you the edges in this direction. If the edge is in this direction, you'll be, or the edge is in this direction, sorry, it was exactly opposite. If your edge is in this direction, this difference would give you. If the edge is in this direction, that's something it can give you this. Say, suppose this you call it as 45 degrees here, plus 45 here, and minus 45. This specific orientations of diagonal edges, it was, I think, I don't exactly remember, could be around 1960s, where that was using of these kernels to compute diagonal edges has been proposed that time. So it essentially finds out diagonal edges which are there at plus 45 degrees or minus 45 degrees. In case of a 3D, you take a Gaussian, 2D Gaussian you would take, and then depending on which edge you want to compute, if it is this, again, you consider this as which should be the center here. Yeah, well, you are convolving it. So 1 minus 1 would flip there. So that you do it, and you will get a kernel similar to this for doing it. One for x direction will be like this, for y direction will be like this. And now second order derivative, if you plot it, you will get a nice mesh plot of inverted Mexican hat. Okay, that is all. This is just a continuation extension of that, and to see how do they look like. Okay, so essentially the f of x plus 1 minus f of x plus 1 comma y minus f of x comma y, if you are doing it, you would see a Gaussian here with center having maximum value and gradually reducing. Now it is done, but with a negative sign, thanks to this minus 1 there. So the Gaussian gets multiplied accordingly. So if you the visualization would be better if you look at it in the mesh plot. That looks something like this. And y would here, if you see the variation is in this direction. Now if you look at it, this in this direction here. That's all. Okay, right. So with that, I am done with the convolution correlation, using them for computing. Initially, averaging filter, smoothing, right? The averaging, weighted averaging, Gaussian filter, followed by that derivatives and gradients. And this has been explained using various kernels, and they were I have explained them how you could you could combine the kernels to create a single kernel and do it. How it gets visualized when it comes to a 2D image has been shown. And also in practice, finally, what you would mainly of very high importance are these two. And if I have to even pick one, I would vote for the Sobel edge detector. In a given image, I want to find out horizontal edges, use the right one there given by Sobel, and vertical edge you will get. Horizontal and vertical edges is like computing. Then the once you compute both, square root of gx square plus gy square, you could think of them in that well, because that's also some Gaussian smoothing has been done. So typically you use this Sobel edges. Okay, you want to sharpen an image, you want to give as an input not just a smooth image, that's what we were doing earlier, but a sharpened image. This can be done by taking a second order derivative. Okay, that will give you a sharpened image. Why is it so? Again, I will not go into a derivation part. If you are interested, please go back and see my medical imaging lectures or any other lectures available there on the net. But I would just try to give an interpretation from here. I guess many of you are taking the deep learning course, right? So did you see something? I was told that Harris corner detector and these things are covered there. So can you make, did you see something like that second order derivative in your Harris corner detector? Is that covered there? Okay.
Yes, sir.
Okay, good. See what is happening here when I take dou square f by dou x square. At any given pixel, I am subtracting its value from x plus 1 comma y. Okay, let me take this as x and this is as y. So from I am taking the sum of that, sum of this, that will give me the dou square f by dou x square. If I write same thing for dou, that will for y, dou square f by dou y square, will take these 2 points. I'll sum. So these 4, since there are 4 points, I'll subtract that minus 2fx. So if I just write for the other 2 points, that will be x comma y plus 1 minus 2 times f comma x comma y minus f of x comma y minus 1. This would give me dou square f by dou y square. If I add them all, it is like sum these 4. Okay, then you just add these 2. That will be minus 4 times f of xy. And here all these 4 points will be there. From that I subtract this. Notice here, when this pixel is very different from the other, that is where you could expect there is something important, edge information, or to be more precise, this is referred to as a corner point, where the variation is there with respect to all the points. So you could use that to compute the points of importance in your image by simply doing, this is referred to as del square of f. Don't confuse with the gradient of f whole square, that you will come across quite a few places. This is a vector. Del square of f is a scalar, unlike the gradient of f, which is dou square f by dou x square, plus you are doing this dou square f by dou s phi square, and this is referred to as Laplacian operator. Once you do it, higher this value, higher the magnitude of del square f. Okay, negative sign and all, you forget. It's just a constant. You take an absolute value. It's not a vector, it's a scalar. That tells you the point being that value being high means that's where there is a kind of edge is there. Okay, this is the expression I have written that. Now I can, if I have that, and then I get this and these points only, I would add it to the original image. Okay, these points only I would, let me put it this way, since I'm not going into the details of this. If I'm going to increase the intensity, this image I'm going to add to the original image. So if I compute these bones, Laplacian would give me this, original plus Laplacian would give me a much brighter image. And of course, it would also highlight or enhance the noise also. Then you could use Sobel to remove those spurious regions. But essentially, through this process, you start with an image like this and end up with something. Then you use other transformations we have learned also, like gamma transformations, and you could get an image which is of very good contrast, and which otherwise are not visible, you can make them visible and you can make your image sharp. Okay,